So we organize equilibrium problems with things called ice tables. And the easiest way to introduce what an ice table is to give you an example problem that we're just going to go through. Now, as always, when we go through the example problem, it's important to write down, what's being said instead of just what's being written down. Essentially, what we're going to have here is a reaction. 2NO2 gas is in equilibrium with N2O4 gas. And we're analyzing a problem that gives us some information. And so we have to interpret the information given in the problem and organize ourselves. And like I said before, the easiest way to do that is with ice tables. Okay, so let's just go through this and I'll explain what an ice table is in the context of this problem. So for the reaction below, there's an initial concentration of N2O4 that's given. All right, and it's 0.125 molar. At equilibrium, the concentration of N2O4, the same species but now at equilibrium, is 0.0750 molar, right? Determine Kc. So for equilibrium problems, there's initial conditions that are given, there's equilibrium conditions that are given, there's a change that occurs to go from initial amounts to final amounts. And so that's what an ice table actually entails. Like that's what is inside an ice table. So what we do when we make an ice table is next to our reaction, we write the word ICE. Now, what do each one of these stand for? I stands for initial. So we're going to put our initial information there, right? C stands for change. And E stands for equilibrium. So for every equilibrium problem, there's some initial conditions that are given. And then what you do is you enforce a change to get to equilibrium. And we've kind of gone over that concept before when we first introduced equilibrium. And now we're going to see it play out mathematically. Okay, what we do inside our ice table is, I like to put a dash here. We look at the reactant side and the product side, and we fill in the information given in the problem. So what we have right now is a situation where N2O4 initial is this value right here, 0.125. Now, I'm not going to put units in here. I'm going to realize that the units are going to come from what kind of K I have, whether it's a Kc or Kp. And, I'm using a Kc, right? I'm trying to determine a Kc, so this problem's about Kc. So I'm going to populate, right, my ice table with molarity information. So I don't even need to write it in because I know ice tables filled with molarity. I'm going to be able to relate it to a Kc. Now, the other bit of information that we have here is an equilibrium amount of N2O4. We have that this is 0.0750 molar. Again, I'm not going to write in the units. Now, what you'll see in an ice table is a lot of information will be missing, but a lot of information can be inferred, okay? Number one, when you read a problem and you're not given information about a species and its initial amount, you can assume that it's zero, and you can only do that for the I, right, for the initial amount. So this reaction is essentially set up with only N2O4 present, right? That's an assumption that's made in a lot of problems. So if you don't see anything about a species initial amount, you can assume that it's a zero, right? Change. Now from before, from a previous video, how do we go from I to E? All right, we do a Q versus K check, all right? And that'll tell me at equilibrium, right, whether the reaction has shifted to the left or the reaction has shifted to the right. So once we get our ice table set up, right, and we have to remember our goal here is to determine Kc. Once we get our ice table set up, what we have to remember about our ice table is that I information in this spot can get us Q. And most of our problems start with, all right, a Q versus K check. Now, you might be saying to yourself, just looking at this already, that you know which way the equilibrium shifts. You see that you have a starting amount of N2O4 that decreases as you go to equilibrium. But let's just practice this. Let's just make sure formally we understand where these numbers are coming from. And a Q versus K check is so important that we're going to practice it here. So if I was going to calculate a Q, all right, Q comes from initial information. So it's going to be N2O4 initial, all right, raised to the first power, divided by NO2 information initial squared because of the stoichiometric coefficient. So this looks like 0.125 over 0. It looks like infinity. So it's a situation where we don't need to even know K, and we don't know K. We have to actually calculate it in the problem, all right? We don't need to know K to see that Q is infinity. So whatever K is, Q is definitely bigger than K. So in situations where Q is bigger than K, which way does the reaction progress? The reaction progresses from products to reactants. There's too many products, all right, in your initial conditions, and you have to get to an equilibrium with less products. This now, all right, so just to recap, I gives us Q, which tells us the direction of the reaction. C then, we can fill out. And what C tells us is the change. The change is based off of knowing the direction. So what's going to happen here? Is this going to go up or is it going to go down? Well, if we see that this arrow based off our Q versus K check is shifting things to the left, this is going to go down. So I'm going to represent that with a minus X, all right, a minus X. Now, if this side of the dashed line, the products are going down, what's going to happen here? These are going to go up. Now, if this is X, right? Can everybody see that stoichiometric coefficient here? These stoichiometric coefficients matter. So if this is going away, right, with an X, this would be added with a 2X because of that stoichiometric coefficient. So I information gives you Q versus K, tells you which way the equilibrium is shifting, all right? Now you can fill out the change, and you're going to use X's here, all right? And you're going to decide based off the stoichiometry, all right, this is a minus X and this is a plus 2X. On these dashes, right, so the reason I like to put dashes here is just do a quick little check. On one side, you should see all negatives, and on the other side, you should see all positives. So then how do we get EQ? So our equilibrium line is always I plus C equals E, all right? I plus C equals E. So in this case, I have 0.125 minus X gives me this number. That's actually really useful. We're going to be able to determine X, all right? Here I have 0 plus 2X, all right, gives me E. So what's 0 plus 2X? My E is 2X, right? And just because it's important and it's a process you're going to follow over and over again, I gives you Q info, determine the direction. That tells you how you're going to fill out your change part of your ice table. From there, you go I plus C equals E, I plus C equals E, and now you have everything organized to solve and finish any problem that you have involving calculations involving equilibrium. So how do we go about solving this? Why is this all the information that we need? I just made a pretty profound statement there, but now we kind of need to prove it to you. Remember how I information could be used to get Q? E information, right, which stands for equilibrium. E information gives you K, right? E information gives you K. So if I make my K expression here, right, it's going to be, okay, yet from previous videos, I need to know N2O4 at equilibrium. Oh, wait a second, that's right in my table. I need to know NO2 at equilibrium. That's in the E spot of my table as well. Oh yeah, and then based off the stoichiometry, I need to square it. My whole goal here is to calculate Kc for this problem. My N2O4 equilibrium is 0.0750. My NO2 equilibrium is the quantity, 2x, whatever that equilibrium is here, you square it. It's not 2x squared, it's quantity, 2x squared, all right? Okay, well, great. So then if I need Kc, all right, all I need to do with the rest of this problem is to determine what x is. And so if we go back, now having things completely organized, and we look at this part of our ice table, all right, one important thing for filling out ice tables is we know that I plus C equals E. So essentially from this expression, we have 0.125 minus X equals 0.0750. because I plus C equals E, I now have a way to solve for X. There's going to be a ton of different unknowns, okay? Any part of the ICE table could be an unknown, but you always fill them out in the same way and you organize yourself in this manner. Just remembering the same principles. Like I said, if you can get this idea down for this, the same principles apply for any problem. So we can easily solve this for X. And when I do this math, I get that my X is 0.050. I know that's molarity, all right, because I remember what units were inside here, but I don't really need that because remember, we're always going to report our Ks without units. So now, if I know X, the only unknown in this expression right here is K, and that's what I was trying to calculate. So K is going to be equal to 0.0750 divided by 2 times this is 0.10, and then I have to take that 0.10 and I have to square it, okay? I'm going to remind myself that there's 2 significant figures here. K's come from equilibrium measurements, so significant figures definitely matter. I plug this into my calculator, and what I get out is a KC that's 7.5, okay? That finishes the problem. I mean, if there are some interpretation parts to it, what does a KC mean 7.5 really tell you? It means that the product should be favored at equilibrium, right? And that's kind of what we saw. The reactant concentrations were 0.05. The the product concentration was 0.075, okay? So again, organization through ICE tables is a key tool that we're going to use again and again. Let's do another example together from the beginning and try to just analyze. This is actually a simple example, but again, I'm going to show you how we can organize our thoughts with an ICE table. So for the reaction below, Kc is 55. Right? And what they want to know is determine the concentration of H2 at equilibrium if the concentration of F2 at equilibrium is 3.1 times 10 to the minus 3 molar, and the concentration of HF at equilibrium is 2.7 times 10 to the minus 3 molar. The reaction that they give is H2, which is a gas, plus F2, which is a gas, is in equilibrium with 2HF gas. So again, it's about staying organized. It's just about making sure you understand the information that's given and where it goes in an ICE table, all right? So right next to this, I'm gonna write ICE. We remember that we have that whole bag of steps. We have that whole series of steps that we wanna take, the bag of tricks that we might need, all right? But we're gonna organize our thoughts with an ICE table, okay? So for the reaction below, okay, so this time they give me a K. Determine H2 equilibrium. So that right there, right here, the E spot under H2, that's going to be my unknown. All right. Oh, I'm given F2 equilibrium. I'm given that this is 3.1 times 10 to the minus 3. I'm given that HF equilibrium is 2.7 times 10 to the minus 3. Well, hold on a second. Do I really need to fill out anything here? And the answer is no. If you remember from last example that we gave, or the last example that we did, E information, right, relates to K. And so I already have the situation where my unknown right here, right, I'm going to call it X now instead of a question mark. I have everything I need to build a K expression with one unknown because the E information relates to K. So in this case, it's kind of nice to organize our thoughts with an ICE table, but then we fill out E info and we realize we're kind of there to go ahead and jump to the math. So you don't always need all those steps. You need to know them in case you do need them all. But for a problem like this, we can organize our thoughts by saying, okay, well, 55, which is Kc, right? This has to be the concentration of HF, which was our product, right? At equilibrium squared. Oh, I got that. They gave me a number, right? Over the concentration of H2. All right, let's write this symbolically first, sorry. Over the concentration of H2 raised to the first power at equilibrium and the concentration of F2 raised to the first power at equilibrium. If you look at the reaction that we were analyzing, this is the appropriate K expression. So 55 equals 2.7 times 10 to the minus third molar. We don't write in the molar, all right? Oh, based off the stoichiometry, you have to square it. The H2 equilibrium information is X, right? And the F2 information is 3.1 times 10 to the minus third molar. So here's an equation. 55 equals this. Oh, just solve for X. And you can practice this math on your own. But when I do this, what I get for X is I get that X rounded to correct significant figures is 4.3 times 10 to the minus 5. Now what the problem asked us for was the concentration of H2 at equilibrium, which is our X. But we want to be formal about presenting it. So now that we're done the math, what's the units for concentration? It's molarity. So determining your X, you're like one step away from the answer. If you're asked to calculate a molarity or a concentration or pressure, make sure you report to the correct units or with the correct units. So the reason I like to show this example is you don't always need to fill out an ICE table, but still it keeps us organized, and realizing that E information relates to K sets us on our path to build our equation and solve for our R unknown. The last example in this video I'm just going to give myself a little bit more room at the top here. Okay, the last example in our video involves the decomposition of a solid. And so what we're going to do is we're going to be given a reaction. So for the reaction below, Kc, so we're going to give a reaction and a Kc. Oh, sorry, Kp this time. Sorry, Kp is 1.81 times 10 to the minus 4. All right. If 5 grams of the solid reactant are placed in a enclosed vessel or an enclosed vessel, what is the total pressure at equilibrium? Okay, what's the total pressure at equilibrium? And then here's the reaction that we're going to analyze. It is NH4HS solid is in equilibrium. And I know that's written weird. They're kind of showing you that it's as a polyatomic ion attached to a polyatomic ion, but it's a solid species, okay? It's breaking down into NH3 gas and H2S gas, okay? So we have some initial information given about the solid. Let's come down and organize our thoughts with an ICE table. Notice we're not given any initial information about the reactants, the products here. We're given information about the reactant. We don't have information about NH3 or H2S gas yet. So here's what we do. Oh, in K expressions or in Q expressions, what do we know about solids and liquids? They don't have concentrations. They actually are not involved in our equilibrium calculations. We know in K expressions or Q expressions, they're replaced with 1. So what we do whenever we see a solid or liquid is we put a big X through our ICE table to remind ourselves that, nope, there's no concentrations here. There's no pressures. Remember, we need concentrations or pressures inside these ice tables. So we can't have that for a solid, big X. We don't do anything with it. You might be asking yourself, then what do we do with this 5 grams? We don't do anything with it because essentially it's not affecting our calculation at all. All right. Well, so then how do we populate the rest of our table here? All right. Well, are you given initial information about NH3 or H2S? No, you're not. And if you're not given that initial information, then you can assume that what we have is a situation where there's 0 starting amount for each. Now, because for this problem, we are given a KP, right? What we're going to remind ourselves as we do our math is I'm actually populating this with pressures, okay? If I use a KP now, ice tables have units and pressures. And when I say units of pressure, I mean we're going to use atmospheres for our pressure unit. So what do we do to fill out the rest of our table? I information can be taken and put into an expression for Q. So what does Q look like here? Q looks like pressure of NH3 times the pressure of H2S. Oh, and what do we do with solid? We replace it with 1, right? So we see here that Q is equal to 0. Let's compare Q and K. Q is definitely less than K. So do we have enough products? No, we don't. So our I information here tells us that the reaction is going to progress this way. I information we use to figure out a Q versus K. Q is less than K. That's the way we're moving towards the products. So now I know how to fill out my C, all right? This looks like it has a stoichiometric coefficient of 1. This is a stoichiometric coefficient of 1. We're moving this way, so I'm going to get a plus X here and a plus X here. So then how do we get E information? I plus C equals E. I plus C equals E. And now for this problem, do we have a K? Sure we do. Is this 1.81 times 10 to the minus 4? Let's just give us some room to write. 1.81 times 10 to the minus 4. If you think about the K expression, remember, K information comes from your E slot of your ice table. So this is going to be the pressure of NH3 at equilibrium times the pressure of H2S at equilibrium based off of what we know from previous videos. Well, this is going to look like an X, and this looks like an X, so this looks like an X squared. And so real simply, we get that X is 1.81 times 10 to the minus 4 to the 1/2. Or we square root 1.81 times 10 to the minus 4 to get what X is equal. So our X here, in this case, when I put that in my calculator, all right, and it looks like I rounded a little bit too early. It looks like 0.0135 atmospheres. And I know it's atmospheres because I used a KP, all right? Let's answer the question now, though, all right? The question asks us for the total pressure at equilibrium. And there will be instances like this where you have to remember some things from bonding. X is the pressure of NH3, and X is the pressure of H2S separately, right? These two gases are in a vessel with each other, okay? So that means that we know how to get a total pressure. We can use Dalton's law, all right? Dalton's law of partial pressure says the total pressure at the end of my reaction is going to be my PNH3 at equilibrium plus my PH2S at equilibrium, all right? Each one of these is an X. So for Dalton's law, we get that the total pressure is going to be 2X. So finally then, you might be asking yourself, why isn't the solid considered at all? Can solids have pressure? Nope, only gases. What do we do with the solid in our ice table anyway? We just X it all out. What are the two gaseous species inside our reaction? They're the NH3 and the H2S, right? So we're in a position now where our total pressure is equal to this plus this, which is the same as 2 times this, and we get a total pressure of 0.0270 atmospheres. Okay. So again, this was a nice example to do because we were solving an ice table problem. Again, we're solving an equilibrium problem organized through an ice table together again. We also remember some things from bonding or your first semester course, like pressures are going to add. I hope you can see what I mean here. This at equilibrium, this at equilibrium, right? And so if we make this much gas and this much gas, the total pressure is going to be these two things added together, and we finish the problem from there, all right? In our next video, we'll do some more practice with this, but this gives you a good sort of basis for going and attacking problems with ice tables. And so that's how you want to sort of approach any problem that needs organization with respect to getting to an expression for K that involves variables.